Let's say you want to design an open box for a company. It should have a square base and 4 faces, with a total surface area of 108 square inches. How will you design it to maximize the volume of the box? What dimensions should you choose? Yes, today we will be talking about optimization. And before we get into this problem, I want to introduce Extrema to you. And here we have the graph, y equals to x cubed minus 3x squared. On the graph, we can see that the origin seems is the highest point on the graph, and the point to -4 seems is the lowest point on the graph. Well, if we consider the whole function, there are many more points above or below these 2 points, so they are not necessarily the highest and lowest point on the graph. However, we can see that there are relative maximum and a relative minimum, and together they're extrema of the function, and the x value there will be called the critical numbers. If we substitute the critical numbers into the function, we'll get the point of maximum and the minimum. These critical numbers will help us when we want to find an optimized result, a maximum or a minimum. But how can we get the value on these 2 points if we don't have a graph? Well, here we need to do some calculus. First, let's draw tangent lines at these 2 points. We can see that the tangent lines are horizontal, therefore the derivative there will be 0. So in order to find the critical number, we only need to know where on the graph the first derivative is 0. So let's first take the derivative of the function and set it up to 0. And we can find the same answer. The critical numbers are 0 and 2. However, if we really don't have the graph, then we need to do a test to check if they are actually critical numbers, which means to draw a sign chart. So let me remove the graph for now and go to the number line. We'll write 0 and 2 on it as their critical numbers. And then we will test the number between them to see if the derivative is positive or negative. So let's choose 1 for a simple reason and substitute it into the equation, and we got -3. Here the negative number means the derivative is negative between 0 and 2. So the function is going downward between them. And then let's substitute a number greater than 2 and see how the derivative goes. Let's say 5, and we got 45, a positive number. This shows that the function is going upwards after 2. So together it would mean 2 is the minimum point, just like what we see on the graph before. And let's test a number less than 0, and you can guess the answer already is positive, just like the graph before is sloping upwards, and this means 0 is a maximum point. Now let's go back to the problem that we have started with. Here's the open box which has a surface area of 108 square inches, and we will try to find the dimension that we have to choose in order to produce a maximum volume of the box. First, we need to set up some equations to work with. For example, base plus 4 faces equal to 108 square inches. And then we can rearrange this equation for each. Also, we can get the volume equals to base squared times height. This is the equation that we want to maximize. Here are the 2 equations that we have set up. We will first substitute h into the volume equation. Now we can simplify the equation and we got this. And then we will do the derivative and set up the derivative equal to 0. After simplify, we got b equals to plus or minus 6. However, base is always positive, so b equals to 6. And 6 will be our critical number. Now let's go to the number line and test to see if it is a maximum point. If you substitute any number less than 6 and greater than 6, like what we did before, you will find the derivative is positive at the left side of 6 and the derivative is negative at the right side of 6. This means 6 is the maximum point. Now let's go back to the height equation and calculate the height. The height is 3 inches. Therefore, in order to maximize the volume, the dimensions have to be 6 times 6 times 3 inches. And we're done. Thank you for watching.